Okay, so let's continue with the second talk of the day by Adrian, and he will tell us about a Krylov space odyssey.
Okay. So thank you very much for the invitation. The picture is not really related to what I'm going to talk about, but I just find it remarkable that we are having a conference in a venue with such a rich history, and I wanted to acknowledge it somehow. But let's just get to the physics. Okay. So yes, I'm going to speak about the C word, which is complexity. So for the non-initiated, there has been an increase in the interest on complexity in the field of holography for the last couple of years, which mainly dates back to a question, I guess, asking, which is what is the boundary observable that describes the growth of the black hole interior, or the Einstein-Rosen bridge, in other words. On the left, I give a schematic depiction of what would be the Penrose diagram of a two-sided black hole in ADS, where we can see some space-like hypersurfaces that seem to kind of expand in the upper half of the diagram as boundary time increases. So how can we describe this in terms of a quantity in the boundary theory? It should not be complexity, at least in this case that I'm giving as an example, because we have a system that is in thermal equilibrium. Sorry, it could not be entropy. If this system is in thermal equilibrium, so entropy should be basically constant. So the proposal is that it could be complexity, whatever complexity is. I will not speculate on how specifically you compute this quantity in the bulk, but I will try just to give an overview of how we can define, how can we quantify complexity in a manner that is sensible to holography. And in particular, by this, I mean that we should find a quantity that has a non-trivial profile up to exponentially late time scales, exponentially in system size, because that's the time scale that up to which the geometric description should apply, and up to which we should extenuate the whole Hilbert space. And more importantly, we should find some quantity that doesn't depend on an external tolerance parameter, because otherwise this would be something difficult to understand in the bulk. But before proposing so, let me give some more detail on what we want to measure. So we want to measure the complexity of states or of operators. So a priori, we could be interested in computing the complexity of the evolution of the thermofield double state, which is a state that is dual to this two-sided black hole in the Schrodinger picture. And this would be probably something interesting, but even richer is operator complexity in the Heisenberg picture, because this is a type of quantity that appears when we study the framework of the so-called butterfly effect. So when we test the stability of the thermofield double state under some perturbation that we induce by inserting an operator that generates an infalling particle that creates a shock wave and therefore distorts the Einstein-Rosen bridge. So the time scales that are going to appear are wider because we can have access to very early time scales, so the scrambling time, logarithmic in system size. And this should also have some effect up to the exponentially late times when we start to probe the fine-grained structure of the spectrum. So we choose in this case to study operator complexity in the Heisenberg picture for these reasons. Now, what is the complexity that we're going to study? It's going to be Krylov complexity, which is a notion that was actually well known in the condensed matter community for a long time. And it's basically a notion that is adapted to time evolution intrinsically. Just to set the framework, we're considering some Hilbert space with dimension d. And because we're going to see and to study operator complexity, we go to operator space, which is going to have dimension d squared. So in this space, time evolution is generated by the Liouvillean superoperator. So it's an operator in operator space that acts on a target by giving the commutator with a Hamiltonian. And just by having a glance at the expression of the time evolution of the Heisenberg picture, we see that at an arbitrary time t, the time evolution of the observable is going to be contained in what we call the Krylov space, which is just the linear span of all the nested commutators of the Hamiltonian with the operator, or in other words, arbitrary powers of the Liouvillean acting on the operator. This is the minimal subspace of operator space that contains the time evolution of the operator at all times. And it should have finite dimension because it's a subspace of operator space. So the task that we have now is twofold. First, we would like to see some structure of this space. And in particular, we would like to compute its actual dimension that I call K here. And then we would like to study systematically time evolution. So how this space is gradually explored by the observable, and try to define a notion of complexity based on that. So the first question is actually easy to answer if we look at the spectrum of the Liouvillean. So I denote states in operator space by this smooth ket notation. And we can easily see that the state given by the ket bra of energy eigenstates of the Hamiltonian is directly an eigenstate of the Liouvillean. And the eigenvalue is just the corresponding energy difference that I denote by omega. So if we use a spectral decomposition of our initial conditions, so the initial observable, we can see that an arbitrary power of the Liouvillean acting on this state of operator space just modifies that linear combination by giving me the corresponding power of the concerned energy difference in each term of the linear combination. And because we have arbitrarily many powers of the Liouvillean in the Krylov space, we just conclude directly that the Krylov space dimension that we were seeking for is given by the number of non-zero eigenspace projectors of the operator. So this immediately gives an upper bound for the Krylov dimension, which is actually smaller than d squared. It's always strictly smaller than the dimension of operator space, just because the zero phase is always at least default degenerate. We just get a zero in the energy difference whenever the two indices are equal. So this upper bound is actually interesting because in the derivation, we have seen that it's very sensible to the structure of the spectrum of the Liouvillean. In particular, we can conclude directly that this bound is directly saturated by ETH operators in chaotic systems, because due to level repulsion, there's not going to be degeneracies in the spectrum in general, apart from the unavoidable degeneracy of the zero phase. And the operator is going to be dense in the energy basis. And furthermore, any degeneracy or any zero matrix element of the operator in the energy basis is just going to reduce the Krylov dimension. So this seems to be a quantity that is very sensible to how the operator is intrincated in the spectrum of the Liouvillean. Once we have this, we can move on to try to study time evolution. So how in particular the operator explores Krylov space. And for this, first, we need to give an orthonormal basis for this Krylov space, given a choice of inner product. So this is achieved by the well-known Langsos algorithm, which takes our initial set of arbitrary powers of the Liouvillean acting on the initial condition and outputs the so-called Krylov basis, which is an ordered basis whose first element is actually equal to our initial condition. And then the nth element contains up to n powers of the Liouvillean. So it still retains some notion of ordering similar to the ordering that we had in the starting set that we have orthogonalized. And more interestingly, we find that the matrix expression of the Liouvillean in these coordinates becomes automatically tridiagonal, where the secondary diagonals are given by a set of coefficients, which are called the Langsos coefficients, that are directly given by the algorithm. So this is interesting because we have mapped time evolution in Krylov space to a one-dimensional hopping problem, no matter what Hamiltonian we started from, where we have a one-dimensional chain whose sides are just the Krylov elements, and the hopping amplitudes are just governed by the Langsos coefficients. So studying time evolution in this chain is going to amount to consider the evolution of a wave packet, which initially is peaked on the left edge of the chain, because this is the first Krylov element, so the initial condition, and which gradually is going to start moving to the right and spreading at the same time. So what I just said in words is captured by this first equation in the slide, where phi n's are precisely the coefficients of the linear combination that describes O in terms of the Krylov basis, and this is the wave packet that we want to study. And here's where we can propose the notion of complexity that we were looking for. So Krylov complexity is defined by the average position of the wave packet along the Krylov chain. So the bigger Krylov complexity is, the farther the operator, the wave packet is in the Krylov chain, which means that it's deeper towards its future time evolution. And likewise, another interesting quantity we can define is Krylov entropy, which is the Shannon entropy of the wave packet with which we describe the evolution of the operator. So there are some expectations that come from asymptotic analysis of the behavior of the Lanczos coefficients in maximally chaotic systems. And it's been proposed that in the strict thermodynamic limits, the Lanczos coefficients should grow as fast as possible. So they behave as some sort of velocity profile in this Krylov chain. So the faster they grow, the faster the packet evolves towards the right. And this implies an exponential growth for complexity. It was later proposed that for ETH operators in chaotic systems, post-scrambling dynamics should be governed by the phenomenon of saturation of the Lanczos coefficients, which itself decreases the growth of complexity and makes it grow linearly. However, the question is, what are the finite size corrections to this, and how does the system actually know that the Krylov dimension is finite? And therefore, how does complexity saturate at exponentially late times? So this is what we wanted to ask in our project with our collaborators in the Hebrew University. And for this, we took the SYK Hamiltonian in the case of four-side interactions, and the target operator, which is non-extensive in system size, which is just a hopping operator between two sides. So we just solved numerically the Lanczos algorithm, which sounds easy, but it's not, and analyze the results we obtained. So the first thing we can say, as you can see in the plot on the left, is that the Krylov space in this instance of SYK saturates its upper bound, as we expected, because we have a system that is maximally chaotic with level repulsion, and where the operator that we studied satisfies the eigenstate thermalization hypothesis. We did see some quasi-linear growth at the beginning of the sequence, as expected, but the predicted plateau gets actually modified by a very slow decrease towards zero at the end of the Krylov chain, which is actually a non-perturbative descent. This is actually something that one should obtain, because the Lanczos coefficients cannot remain constant up to indefinitely late times. And this is what is going to yield the saturation of complexity at late times. So the complexity profile that we obtain is indeed a profile that starts growing, one could say exponentially, at least quickly at early times, and which transitions to a linear growth post-scrambling. This linear growth slowly gets corrected due to the decrease of the slow decrease of the value of the hopping amplitudes, and eventually K complexity, we see that it saturates at a value that equals, I didn't write it in the slide, but equals precisely half of the Krylov dimension that we obtained. So this is a result of the fact that the wave packet becomes at late times completely a uniform distribution in Krylov space. So the average position is equal to the half of the Krylov space dimension. And we also have an interesting profile that results for K entropy. So K entropy starts growing as fast as it can at early times, which is linearly in this case, and transitions to a period of logarithmic growth after scrambling up to its saturation value, which is again linear in system size, because basically we have a uniform distribution. So this is the results we get for our numerical analysis in SYK, and we can just jump to the conclusions. So we have studied K complexity as a notion of complexity that does not depend on an external tolerance parameter. It's just a notion that is adapted to time evolution and that describes the ergodic exploration of the Hilbert space by an initial condition. To our surprise, we did find that this quantity is sensitive to the structure of the spectrum, and which becomes maximal whenever we have a chaotic system. And furthermore, we found non-perturbative corrections to the predicted profile of the Lanczos coefficients. Non-perturbative corrections that are actually crucial for the eventual boundedness and saturation of the complexity. So therefore become crucial at late time physics. There are still some questions that remain open. So for example, I remained agnostic and didn't try to speculate on the bulk interpretation of Krylov complexity, but I wouldn't be pessimistic because precisely we're just describing the successive exploration of microstates of an initial condition as it evolves in time. So this could potentially have an interpretation in terms of a bulk description. This notion of complexity has, however, some problems. It's strongly dependent to the initial condition, which is precisely a result of the fact that it gives a complete basis for the Hilbert space. And so therefore it can change drastically if we change the seed of the Lanczos algorithm. And it's also not clear how to define a similar notion for the case in which have a time-dependent Hamiltonian. But most interestingly for us at this point is that it seems that this can be a probe of quantum chaos because of the strong dependence on the structure of the spectrum of the size of the Krylov space. So at the moment we are actually this actually constitutes work in progress, and we hope to be able to say something more about this soon. So thank you very much.
Thank you. Questions? I have a question about, I think maybe it's related to your last point. So how this numerics you did in SYK,
yes.
So how general is it? Like what do you expect to be, which part of this behavior you expect to be generic and which part you expect to be specific?
So yes, maybe I can show again. So what the curve we see for SYK seems to be actually quite universal, and it's a pity that I didn't include it as backup slides, but we also did the same computation for random matrix theory. And what we find is that in the case of random matrix theory, the pre-scrambling dynamics are not so clearly similar to SYK. So in general, one doesn't expect to find universality of random matrix theory at early times. But the most prominent feature that you see in this plot, which is the non-perturbative descent of the Lanczos coefficient, seems to be also present in random matrix theory. So another thing that one could hope to establish is that this non-perturbative decrease of the Lanczos coefficients is actually related to random matrix theory universality, which would agree with the intuition that this is something that captures quantum chaos.
But suppose you have a field theory. So you have
yes. Naively, you could think so, but I think in field theory, you're perfectly allowed to study microcanonical window of the spectrum, right? So then as long as your Hilbert space is discrete, if you place yourself in a microcanonical energy window, then you do have a finite dimensional space where an analysis like this can be performed.
Well, but here, I mean, just by computing commutators with the Hamiltonian, you expect to find that. I don't understand exactly how do you place it.
Yes. So, okay. So, so for studying field theory, maybe let me just glance. The analytical tool that one uses to tackle this problem is actually the existence of a certain relation between the Lanczos coefficients and the two-point function. So because the Lanczos coefficients are actually the secondary diagonals of the Liouvillean, and therefore, if your inner product is the two-point functions, which is basically like a Frobenius norm in operator space, then one can see that the moments of the two-point function are just 0, element of arbitrary powers of the Liouvillean. And therefore, there exists a combinatorial relation between the Lanczos coefficients and the moments of the two-point function. So how one would proceed, the way in which one would proceed in the case of field theory would be to study the two-point function in a microcanonical setup and analyze the moments of this two-point function, and from the transformation obtain the Lanczos coefficients. And this is something that can be done in principle and should yield a sequence that terminates eventually. Yes. Yes, yes. This paper by Sally and collaborators in the British Columbia University, where they actually were studying this, and they tried to apply some renormalization group arguments, where they kind of did agree with the intuition that the non-perturbative descent seems to be a random matrix feature. But there's more to be said.
More questions? Okay, now let's time for the next talk.